Good morning, everyone. Okay, let's wait for a few minutes. Okay, we'll start in maybe say at 9:02 or 9:03. Let others also join in. We'll start in a few minutes.
Good morning, Sanderson.
Good morning. Good morning. We'll start in just 2 more minutes. Okay. There are just 3 people right now. Meanwhile, if you have any questions, you can ask. All right. We'll start in say at 9:04. Okay, I'm just writing some basic Python code to import the data. What do you recommend? Shall we start or shall we wait for a few more minutes? What do you guys say? Shall I think we should start with it. So
Yeah,
I really don't know if somebody will join in or not. Okay. So what I've done so far is just imported the basic libraries, as you can see. Okay. Then imported this binary classification data set where a person, if it's suffering from cancer, the person will have a label as 0 here. Okay. Please note that 0 means malignant. Okay.
Sanderson, if it is
Yes.
okay with you, can you zoom in a bit because
Yeah,
my
sure.
system was
Sure.
already a small. Yeah, thank you.
Yeah. And 1 here means that the person is healthy rather. Okay, so no cancer. Or it's called as benign category here. Okay, so it's a reverse in this case. You can see 0 is the minority class. 0 is the class where people actually have cancer. Okay. All right. So we have to use these 30 features to train a model, and the output is 0 or 1. Okay. So I'm going to show you how to implement. I think we have done random forest, right? So bagging is done. Does anyone remember, like if we have done random forest implementation?
Yes, we have done that.
Okay. So let's start with directly boosting. So I'm going to start with AdaBoost, adaptive boosting. Okay, it's also called as AdaBoost. Okay, so let's implement this directly. So what you have to do is go to the same library, which is Ensemble. Okay, and import AdaBoost classifier. Okay, you can import this AdaBoost classifier. Now, the thing is, you can boost any model. Okay, you can boost any model. Let's call this as maybe say AdaBoost classifier as ABC. Okay. Now, which model do you want me to boost? Tell me. Which model do you want me to boost? Give me the name of any classification model. We will boost that. Can you name any classifier that you have studied? Any classification algorithm?
Decision tree.
Okay, so let's boost decision trees. So default, I mean, if you don't pass anything to AdaBoost classifier, right? Okay, it will by default boost a decision tree only. Okay, if I keep it as it is, so default is a decision tree only. Okay, and default is a decision tree classifier. Okay. But if you want to import it explicitly, you can also do that. So from tree, you import decision tree classifier. Okay, and let's call the model as said this decision tree classifier. All right, and you can say a random state here to get the same results. You can provide other arguments which are you can say the characteristics associated with the decision tree, like pre-pruning and post-pruning heuristics. So you can specify those and boost it on top of that. So I'm going to recommend you something, okay? So when you're going to boost, right? So boosting is, I would say, an extension, okay? So you should boost the best performing classifier, okay? So if you want to actually further improve the performance, first find the best model and boost the best performing model. Does that make sense?
Yes.
So what I'm saying is find the best performing decision tree classifier and then you boost it. In today's tutorial, I'm not going to do that. I'm just going to show you how to boost any model. Okay. So in your case, I mean, whenever you want to implement something, right, find the best performing model using grid search or say randomized search. Use those hyperparameters here in the arguments and then do adaptive boosting on top of it. It most of the times it will give you some increase. Okay, most of the times it will give you some increase. Okay, so I'm going to maybe split this data, or rather, what I'll do is I'll run 10 folds. Okay, I'll run some 10 folds on the given data set. Okay, so since I'm doing decision trees, is there a need to scale my data?
No.
No.
No, right? So I don't have to scale my data, so I'm not going to do that. Okay. So let's define how many folds we want to run. So I want to run say 10 folds. Okay. And let's call this say as SKF. And now you can call this cross-val score. This will give you the results on the 10 folds. Okay. So you have to provide the model. So let's say our model is this decision tree. Okay. This is my model. Let me import this library above as well. All right. And now you will pass the model here, the data, which is in X and Y, the type of cross validation, which is your stratified k-fold, and a scoring metric. Let's say I'm looking at accuracy. Okay. So it will give me 10-fold results. So, I mean, as you can see, it gives me 10-fold results. Okay. But currently, I'm using the default model. I'm saying you should find the best performing model first. Okay. And this is the average performance over 10 folds. It's around 90.686. Okay. Now I'm going to show you like what is the performance of the boosted model. Okay. So once you have obtained the boost, like the best performing model, then you apply boosting on top of it, and it can even give you some more improvement. I'm going to show you on this default model that you obtained, okay, which is this decision tree. So pass this base estimator. Okay, so use this base estimator as the model that you want to boost. So this is my model, right, that I want to boost. So I'm passing this model here. Okay. I'm going to first do it like with the default arguments with default hyperparameters, and then we will try to tune it further. Okay, so I'm going to fit it to my data, or rather, since I'm only interested in doing this cross-val score, okay, I'll get the cross-val score on this ABC. So essentially what you're doing is you are boosting a decision tree, okay, on this data X and Y, and you're doing 10-fold cross-validation with accuracy as your metric, and it will return the average of 10 folds. Okay. Do you see that it has boosted the results?
Yes.
Okay. So boosting is like one step on top of it. Okay. On top of your best performing model. Now, next thing that we'll do is we'll see how to boost, how to fine tune the hyperparameters. Does anyone remember what are the hyperparameters associated with boosting? Yes, people.
Number of number of estimators.
Number of estimators, and there was one more. Learning rate. Okay, so we have, so I'm going to maybe, I think the default number of trees are either 10 or 100. Okay, let me just check. Okay, I'm going to check, okay, how many, I believe it's 10 or 100, something like that. It's 50. Okay. All right, let's use this. So maybe I'm going to start from say 25. I'll go up to 200 at an interval of 25. Okay. So 25, 50, 75, things like that. Okay. And then I'm going to provide the learning rate. I'm going to, so by default, this learning rate is 1. I'm going to check this learning rate, maybe say between say 0.5 to 1, maybe checking 5 values in between. Okay, maybe 6 values in between. So 0.5, 0.6, 0.7, 0.8, 0.9, and 1. Okay, and then I'll call say grid search. So it's not many models that I'm training, so it won't take much time. Hopefully, we'll be able to improve this result as well. Okay. The model is ABC that we have. A model is ABC. You have to pass the parameters, which is in param grid. Then you have to pass the cross validation, which is stratified k-fold, a scoring metric, which is accuracy in our case. Okay, and let's call this as GCV. Okay, and then I'm going to fit onto my data in X and Y. Okay, there's a problem. Oh, let's call it hyperparams. Okay, it'll take maybe 2 minutes. Okay, this is done. Let's see what is the best result. Hopefully, it is better than 91.6. You can see we have slightly improved upon it.
Yes.
So when searching did you a favor, and you can see the best parameters. So learning rate is 0.7 and number of estimators is 175. So did you see when the learning rate was high, how many estimators were there? Just 50, right?
Yes.
And so if you look at the best combination, which is 0.7, so learning rate become lower, right? And what about the number of estimators? It became higher.
Higher.
So when you are having lower learning rate, you will mostly see more number of estimators giving you best results. Okay, because there is this trade-off between them. Okay, so this is how you do grid search with AdaBoost. I'm going to show you now gradient boosting. But before I do that, let me show you something. Okay, you can essentially boost any model. Okay, you can essentially boost any model. All right, you can boost say a logistic regression model. So let me boost a logistic regression model. Say go to sklearn linear model and import logistic regression. So as long as the model supports sample weighting mechanisms, so only k nearest neighbors doesn't support among the algorithms that you have studied. Okay. So you can now boost this logistic regression. Okay, and I'm going with the default one. Okay, I mean you can compare only with logistic regression and doing boosting on top of logistic regression. Okay, so I'll do that also. Okay, just in case. Okay, do you see the boosting results are far better? See, this is the result when I only used logistic regression around 93.85. Okay, when I did ADA boosting on top of it, I got 95.43. So you can see that boosting generally helps. Okay. Now I'm going to show you okay how you can boost, say, support vector machines. So you can do it in the same way, but there is just one difference. Okay. So when you're going to boost a support vector machine, right? Okay. So first of all, that lies in this library, small svm, and the name of the model is support vector classifier. You need to set one argument, which is probability is equal to true. Okay. Otherwise, this is not going to work. Okay. Otherwise, this is not going to work because you need probabilities from SVMs. So this is going to show you what is the boosted performance on this support vector machine. Now you can compare it with the original performance without boosting. This will generally be better. Okay, this will generally be better. Any other model that we have studied that you want to boost?
Can I combine can I do this heterogeneous?
Yeah, I'll show you. So once we are done with, say, this boosting, I'll show you how to do heterogeneous assembling as well. Okay, I'll show you that. I think it is running with this RBF kernel, which takes time. Okay, this is done. So around 93.30414. See, please note that this is the boosted performance of SVM. I have not come. So if you want, I'll do the simple computation with SVMs also. Yeah, just a second. So I'll do with normal SVM also. Okay. Can you see that in case of SVMs, it doesn't work that well?
So for logistic regression, don't we have to first standardize the data?
Yes, then it makes more sense, right, to standardize the data. So what I would recommend is you make a pipeline. Okay. Thank you for pointing this out. So I'll just make a pipeline here. Okay, because it makes more sense to standardize it. So let's do, say, standardization. Okay, and which is there in pre-processing. Because I'm using these process data sets, right? So they are already kind of standardized. That's why you will not see much differences in the performance. Okay. So I'm directly defining the steps here. Okay. Okay, so I've just incorporated your pipeline here. You can see, okay, it actually improved the result significantly. Yes or no? Standardization helped in this case quite significantly.
Yeah.
Okay, I'll do it for the basic logistic regression also. Okay, so that we can have a fair comparison, because this is done without that. See, logistic is actually giving better performance. Okay, like the default one. But boosting is kind of letting it down. So if you basically do grid search on it, right, it might improve the results. So it will be better than this 98.06 for sure. Okay, let's try it. Okay, let's try it. Where were we? Here. So I'm going to just tune the parameters. Okay. This time I'm going to pass my pipeline, which is this. And I have to provide in the hyperparameters that they are AdaBoost classifier hyperparameters. Okay, hopefully this would be better than 98.067. Okay. So boosting typically helps. Okay, it's very rarely that it will not help. So even in the experiments that we are doing, right, this is running with the default hyperparameters. Okay. So and the decrease is not that much. So it might help. Okay, that's why I did this grid search. Yeah. All right, let's see. Okay, what are the results? Just wait for some time. Meanwhile, if you have any questions, ask. Yes, any questions? I'm just making sections so that you can follow it up easily. It's still running. Okay. Let's see if it is done. No, it's still running.
Yeah.
Okay. Meanwhile, it runs. I'll create. First, do you want me to do heterogeneous ensembling, or do you want me to, implement gradient boosting? What do you think
We'll
would be
go with gradient boosting and then
okay? All right, let's do gradient boosting then. So gradient boosting is actually implemented in many different packages. I'll show you the industry packages also, and I'll also show you how to do it in sklearn. Okay, let's just wait for this, otherwise it will not learn. Okay, so I'll just implement it. So you have to go to again sklearn.ensemble, and you have to import this gradient boosting classifier. Okay, so this is one of the gradient boosting implementations. There is one more. Okay, so this is the alternate one, and it's called as HIST gradient boosting classifier. Let's copy paste this. Let's see. Any other questions, like meanwhile, like by the time this finishes? So the purpose here is that we should be able to beat this performance. Okay, 98.067.
98 point. Yeah.
See, at least it would be this much. It will not go down than this.
But without boosting itself, in the logistic regression, the model was doing well and good, right?
Very well, if you think about it. Like,
Yeah, but
uh,
in not every case this will happen. So that we were going with the
no, see, the point is, let's say you're participating in a challenge. Okay, so minimalistic improvements also help, right?
Yeah.
Like if you want to win a competition, if you get an edge by say 0.2%, so
Okay.
that will make you the winner. Okay, so this is like
True.
an extension step. Okay,
Okay.
so find the best performing model, and then you want to increase the performance slightly. So boosting can help there. This adaptive boosting can help there. Gradient boosting is an implementation of it on. Okay, that's only based on decision trees, but this is a generic procedure through which you can boost any model.
Mm-hmm.
Is this done? Still not. Shall I stop it and you can run it? What do you recommend? Or shall I keep it running and wait for some more time?
We'll run and see, Santon, because it's taking more time and we were waiting, right?
Okay. So what I'll do is like I'll just stop it and you guys can try it. Okay. It will certainly beat this performance. Okay. This one. Maybe it will be like 0.981 or 0.982. There will not be much jump. Okay, let me just stop it. Okay. All right, let's implement this gradient boosting. So in gradient boosting, you can directly import your gradient boosting classifier. All right, I'm going with a default model, first giving just a random state to ensure that, okay, you get the same results. And then I'm fitting onto my data. There is no need of, you can say, I'm scaling the data. So I'll just use this. So let's see the tenfold results using this. And let me import this. So this does it around 96.14. Okay. And then let's import this. So these are the two variants that are available for you for doing boosting. Okay, let's implement here I mean, the hyperparameter tuning part of this. Okay, so it's the same set of hyperparameters essentially, but there are a few other things. So you can obviously pass a number of estimators. You can pass. So this time I'll implement grid search. Sorry, randomized search. Okay, I'll just implement randomized search this time. That will save me time. Okay. Okay, I'll do boosting on top of this. Okay, let's provide some more hyperparameters. So one more second, please. So this is called as param distributions here. So you can go with max samples, like how many samples you want. Okay. So I'm going with say some percentage of samples, say 70% to 100%, and taking say 4 values in between. Okay. You can go with max features. Okay. And let's give the same, okay, using 70% up to the entire value, basically using all of them. So I think this is it. So you can go with these parameters and try to get the best results. Typically, you use this also, that makes a difference, okay, min sample split. Okay, this is in my opinion, this makes a subtle difference. So what you can do is maybe take a range of it, starting from, so default value is 1. Sorry, default value is 2. Maybe go up to 5. Okay. All right. There's a problem here.
Randomized search CV in this
Oh,
model.
sorry. Yeah.
And here this maximum samples means that instance bagging samples.
Instance bagging. Yes, this is instance bagging. Like how many samples you actually pick for every model. Okay. And this is feature bagging. So you are still bagging, okay, but the concept that we are using is we are reweighting the instances, right? When we are doing gradient boosting, we are giving more weightage.
Bagging and then we are boosting.
See, bagging is just a way to select your training data. Boosting is, you can say, I mean, you can say boosting. Yes, boosting is like an extension to bagging.
Okay.
Okay, yeah, that is a better way to put it. Okay, 1 second, there's some problem here. Okay, just a second. Instead of max samples, it is called as something else. It's called a subsample. Okay. Hopefully, it should not take much time because I'm doing a randomized search. Okay. It'll take at least hopefully 2 minutes, no more than that. So hopefully we should be able to beat this performance. Even though we are trying for 1 or 2 combinations, but let's be hopeful. Okay, if we are able to beat this. Otherwise, we run it 1 more time and then we see what is the performance that we get. These are your best params and this is the best score. Okay, did we beat it or is the same? This is the same, right? No, it's 7.7, so it's slightly lesser. Okay, maybe 1 sample got misclassified. Okay, it's 96.8389. Okay, 724310. It's just slightly better. It's almost the same essentially. Okay, maybe you run it 1 more time. Let's run it 1 more time and see. Okay, if you are able to beat it. This is not grid search. Okay, This is not that search. You can try with the other one, hist gradient boosting classifier. Okay, and hopefully you'll be able to see a slight improvement there as well. See, because 96.83 is already touching, say, 97%, right? So if in your test set, okay, how many samples will be there in the test set? Think about it. How many samples will be there in the test set? Think about it. So you do see there is a slight boost here right now. Okay. From 96.83, we went up to 97. Okay. My question is this. If you are doing 10-fold cross validation, how many samples will be there in the test set? What percentage? In every fold, how many percentage of samples will be there in the test set? What percentage of it? How many partitions will you create if you are doing 10 folds?
10 partitions.
So can I say in every fold, 10% of the data goes to test set
Yes.
and 90% goes to that. So I'm going to see what is the size of X. Okay. So out of 569 samples, how many of them go to test set in every fold? 57, right? 56 or 57. Okay. Now you are doing 97% of it correctly, almost 96.83% correctly. So what is that number? So if you see about this 0.97 of this 569, or rather, let me say 57. So think about this. See, you are doing on 55 samples correctly. I just increased the percentage by 1 sample. So what did boosting do? What did boosting do here? Think about it. It just increased your performance on 1 sample. Yes or no?
Yes.
But that must be very hard, right? Think about it. Why? Because you're already doing so good. Okay. So it helped by just 1 sample. Okay. If it did it on all, then your performance would be 100%.
So this K-fold will be applied on the entire data set of first
On the
instance
data set.
mapping will be done and then K-fold
No,
will
no,
be
no, no, no. On the 90% data that you have, right? In the train set.
Okay.
See, in every fold, you have 90% data in the train set, right?
Yes.
So from there, the samples will be picked.
Okay.
Okay. All right. So this is your, what we say is gradient boosting. You can try with hist gradient boosting as well. The only difference between these two is what hist gradient boosting does is actually it converts your numerical features into some categories, into, you can say, categorical features. Because, okay, let me ask you this. If you are making a decision tree or any decision tree based model, what type of features do you select so that you get a shorter tree? Think about it. Let's say I give you a choice of numeric feature and a categorical feature. Where do you see more children?
More children will be in categorical.
In categorical feature, right? So if you are creating more children, let's say on a like in the initial levels. So if you create more children there, is it likely that the tree will go like very long?
No, the depth will decrease.
That will decrease, right? So what hist gradient boosting does, it first makes your numerical features into categorical features by just putting some ranges. Okay. And it does it intelligently. If you are interested, you can read about how it does it. But once it identifies or transforms your numeric into categorical features, it then kind of emulates this perception of avoiding overfitting. Because the shorter your tree, you are avoiding overfitting, right? Yes or no?
Yes.
So that's why sometimes it may be better, it may not be better in some cases. So I mean, you cannot say for sure unless you test. Okay, unless you test. But it would be still very, very close to your original gradient boosting classifier. Okay, it would still be very, very close to your gradient boosting classifier. So there are 2 implementations that are available to us. Okay. Now I'm going to show you some industry related packages, though I will not go in very deep because they have a lot of other hyperparameters. But I would recommend that you explore the hyperparameters, read about what to tune actually. Okay, because they will have around 50-60 hyperparameters. So I request that you maybe do some digging, figure out what hyperparameters people try to tune the most, and only do those. Don't use all 50 of them, otherwise a huge chunk in your lifetime would be taken by that. Okay, so just see what others are using and go by that. Okay, maybe do a little bit of digging. So I'm going to show you some packages which are industry standard. So one of them is XGBoost. Okay, it's called as extreme gradient boosting. This was developed by a person named as Tianqi Chen. Okay, it was developed very recently, around 2006 or 7. But it is one of the best performing models, and it can be used for both classification and regression. Syntax is more or less the same. Okay, so what you do is first install XGBoost. If you are using Colab, it may come installed by default. Okay, you have to install XGBoost by this. In my case, it is already installed. Then you need this XGBoost classifier. Okay, and you can then use it in the same way as you do your sklearn packages. Okay, I'm just putting a random state here so that you get the same results. Okay, so you fit it onto your X and Y. Let me get the the tenfold results. Okay, I'm getting the tenfold results with this. All right. So you can see, okay, it kind of does better than your sklearn boosting, right? Yes or no? Do you see that in sklearn boosting that we just did, we reached around 97.01. I haven't even tuned it and it reached around 97.894. Okay, so by default, the default parameters are still doing a good job. Okay, a much better job. All right. But if you tune it further, it will surpass around 98.5%. Okay, so I'll just show you what we say is the hyperparameters. There's a huge list. Okay, there's a huge list that you can use. Let me show you the Python package. So this particular package is available in a lot of languages. So you can use it in R, Java. It's mentioned here, Julia and all that. C++ package is also available. Okay, so let's directly go to the parameters. Okay, so these are the parameters that you can search. Okay, let me go to the directly one second, please. Where is this Python package? Just a second. Not this, I don't need this. I just need the whole library. Okay, just a second, please. I'm not looking for this. Just a second. Yeah, here it is. Okay. So these are all the hyperparameters that you have. Okay, booster, verbosity, validate parameters in thread. These are the parameters. Okay, there's a whole list. Okay, around 50-55. Okay. Okay, so this is like a very extensive package. Okay, so I request you all to please check it out and maybe do a little bit of digging on the web, how to tune it to the fullest. So you don't have to search for all of them. Okay. But this package kind of gives the best results, in my opinion, on most data sets. Okay, on most data sets. You can see, right, there are more than hundreds, I believe. Okay, so I'll just mention it here. Okay, so you can tune the hyperparameters. Okay. All right. So I'm going to show you one more package, which is again very popular. It is comparatively faster on bigger data sets. This is called as light GBM, light gradient boosted machines. You can use it in the same way you can import, say, light GBM as LGB. Okay, and then I have to see the package. Is it called as LGB classifier? Syntax is more or less the same. Okay, syntax is more or less the same. Okay. Just a second. Yeah, it's called as LGBM classifier. Okay, so the syntax is like the sklearn. Okay, very, very simple. So I'll just mention this. Okay, these are all the hyperparameters that it has. So you can say, okay, model is equal to LGB dot this LGBM classifier. And the same way that you do it, right? Do a cross-val score on this. Okay, if you want to put a random state here so that you get the same results. Okay, and I'll just mention the hyperparameters. Okay, from this link. So this is also an excellent package. It works quickly on bigger data sets. XGBoost can be slower. Okay, XGBoost can be slower. Please note this. Okay. You can see that LGBM is doing. The results came out quickly than comparison to XGBoost, but it has a little bit of. That's why I said XGBoost will give you better results in general on most data sets. Okay, but LGBM is needed when you want to train models quickly. Okay, so it consumes less resources. XGBoost does a lot of tweaks to your data. Okay, if you want to be competitive, use XGBoost. If your objective is to just get a good model, then I suggest LGBM, LightGBM. Okay, there is one more, which is an interesting package, which is called as CatBoost. Okay, categorical boosting. This is very similar to your HIST gradient boosting classifier. It converts your numeric features to categorical. Okay, so you install this CatBoost. I think you simply have to write CatBoost. Okay, and the syntax is the same. Okay, 1 second. Okay, I'll just show you. Maybe regressor is at the bottom. Yeah, here it is. Okay, so you can call this model to be this. Okay, and then you can, I think, simply run it. Yeah, so it is giving you your results. Okay, so it is essentially giving you what we say is the 10-fold results. Okay, so every time it runs it, you can set the verbosity to 0. Here, you can set verbose to 0. By default, this value is 1. So it will not show you any outputs. Okay, so it will show you the results of 10 folds that it is running. Okay, just a second. Okay. So let it run. Okay, this is done. This is a performance around 96.83. You can try tuning it. I'll just mention the hyperparameters from this. Just a second. The hyperparameters for this. And they give these are the ones. So these are the hyperparameters. Okay, you can check them out. Learning rate, what was the loss function, the random seed, okay, L2 leaf regression, okay. So these are the, so L2 leaf regression is like the ridge regression variant that you're doing. Yeah, the hyperparameters are here. Okay, these are your hyperparameters. Now, before I go to say any further packages, do you want me to show you heterogeneous ensembling, or shall I complete the packages first? What do you want?
Complete the packages first.
Okay, now let's complete the packages then. So I'm going to show you a package where you can directly use 30-35 models. So that package is called as Lazy Predict. So you have to install this Lazy Predict. Okay, this will show you 25 to 30 models directly. Okay, 25 to 30 models directly for both classification and regression. Okay, so I'll just borrow the syntax from the library. Okay. See, using the libraries is actually super easy. You just take this. Okay. They're essentially using the same data set as ours in the example. Okay, all right. Okay, let me explain what this does. So what we are doing right now is like we have taken a data set, which is the breast cancer data set. Okay, and then we are splitting it into two parts, the train and test. Just a second. So we are splitting into two parts, the train and test. Thereafter, we are applying this lazy classifier. So this lazy classifier has the implementation of around 30-35 models that you will see in a bit. Okay. Verbose is equal to 0 means that it will not throw you any what we say is text material which is being generated when the model is trained. If you set it to 1 for every model, it will throw you something. Ignore warnings is true. Sometimes the data might not be perfectly valid for some of the models. So if you set it to false, then it will show you warnings. Okay, this model was not trained. Even if a model is not trained, like it doesn't include it in the results, it just skips it. Okay, and if you want to provide a custom metric, you can use the make scorer function. Do you remember I showed you like we had seen the implementation of a custom metric, right?
Yes.
So you can pass that custom metric function here. Okay, so if you want your own metric for a classification task, you can pass it here. Okay, then you're giving X train, X test, Y train, and Y test. So it will use the training features to train the model, and the test the train outputs to train your model. These test features and test data will be used to, you can say, evaluate the performance of the model, and 3 to 4 different metrics will be shown to you. So it will show you 3 to 4 different metrics for each of the models. Okay, let's see. Okay, just a second. This Y is capital Y in my case. So it is currently training around 29 models. This is the result. So the first result, the best result is currently linear support vector classifier. You can see the accuracy is this. Balanced accuracy is nothing but the accuracy of class 0, accuracy of class 1. Add those accuracies, divide by 2. That is balanced accuracy. Do you think it is the same as like the total accuracy?
No.
No, right? So balanced accuracy is like the average of individual accuracies. Okay, it's not the same. Okay, this is ROC AUC. This is the F1 score, the harmonic mean of precision and recall, and this is how much the time it took. So it is showing you for around 29 models. What are their results? Now you may ask, sir, it's not tuning, right? It's giving me the performance from the default models. So how you can use this package is, you just look at the top 5 to 10 models. Okay, you just look at the top 5 to 10 models. The idea is, if you are participating in a challenge, you can combine these models together, or you can, what you do is, or you can tune these models by doing this hyperparameter grid search. Okay, and you can get the competitive edge on top of your peers. So this particular, you can say, library helps you run the models with the default parameters. So is this good enough? Just from a very early perspective, it gives you an idea, okay, which models are doing better. And did you realize it ran pretty fast? Yes or no?
Yes.
So it's a really good package to look at. I will recommend you even a better package than this, which is called as PyCaret. Okay, so you have to install this package first. This is the package which is used by most industry people if they are working on a GPU cluster. Okay, if they are working on a GPU or even a CPU cluster.
I have a question in
Yes.
the above thing. The above model, like this shows me the names of the model, right? So
Correct.
this means that I'll apply linear SVC model,
Correct.
multiple linear SVCs model, and this is the
No. This is the, what it did was, like in sklearn, there is this package called as linear SVC. Okay, so it used linear SVC, trained the model on the train set, and evaluated the results on the test set. And that is what you are seeing here. So it did not do any tenfold cross validation, no nothing.
Okay.
Okay, what it did was, like, it just split the data into two parts. We split the data into two parts explicitly.
Yes.
What was the percentage? We must have specified it, right? 50% data goes to training, 50% in testing. Okay, so it is only using 50% of the data in training and 50% in testing. So this kind of gives you an estimate of what models might do well.
Okay.
Okay, so you don't really have to fine tune all of them, right?
So then after looking at this data, which like the top models which I take, then I do boosting with those models.
Yes, you can see boosting is later on. Okay, first you will fine tune these models. Okay, let's talk about logistic regression. So it is running logistic regression with no hyperparameters. What are the logistic regression hyperparameters, if you can remember? You can provide the penalty, yes or no?
Yes.
You can give the alpha values. It's not alpha, it's actually C in logistic regression. Okay, is the inverse of alpha.
Class weights.
Yes, so you can give class weights. So that way you can make it better, right? So once you identify the best model of logistic regression, then you can do even boosting on top of it.
Okay.
Okay, so this is like the first step, which helps you decide, okay, which models might do better.
Okay.
And from those models, you do a grid search to make them the best performing in their own respective individuality. And after that, you do boosting on top of it to get one more. You can say that you are doing one more up. Okay, so that's how you're doing it. All right. I'm going to show you this package, which is pip install, say this PyCaret. So this PyCaret also does the same thing, but it can give you tenfold results directly. It can impute directly. Okay, so it is like an end-to-end pipeline. So if there are missing values, you can specify what to impute it by. So if there are real values, well, how would you like to impute it in general? By mean, right? If there are categorical value, you would like to impute it by mode. So you can specify all these things in this package itself. I'm going to show you how do you use this package. The syntax is quite complicated, so that's why I have this here. This is for regression. I'm going to just show you how to use it for classification. The only thing that you have to change is change regressor by classifier. Okay. Wherever you see a regression, you change it to classification, and wherever you see regressor, change it to classifier. Rest the syntax remains the same. Okay. All right. So I'm going to do classification, right? So let me import from classification. Let me import this classification experiment. All right. So here also, this will be classification experiment. Okay. Now, there is one thing that is very specific to this. You have to put all of your data in a data frame. Okay, you have to put all of your data in a data frame. So, do you remember my data is in what variable? My data is in what variable? X. Yes or no?
Yes.
My features are in X, right? Which I'm splitting it into, which I split it into train and test in the previous code. So this is my data frame. I have to specify the output as well. Let me say the output is say output, and this output is my Y. Okay. How do you use this is like this. So provide the setup, okay, provide the data frame on which you have the data, in which you have the data, give the output value, the name of the output column. So what is the name of my output column?
Output.
Output, okay. And this is the percentage of data that you are going to use for doing cross validation. This is the percentage of data. So 80% of the data will be used for cross validation. And whichever results that you have, okay, so if you, let's say if you just skip it, so then entire data would be used. Okay, so I'll just show you. So let it get ready. Okay, just a second. Okay, so it shows you, okay, what it is about to do. It says that I have around this is the session ID. This is the column name output. We are doing binary classification, so it automatically identifies what is it that we are trying to do. This is the data shape, original data 569,31, because I added this output column to it. By the way, there are 30 features in this data. Okay, so it has transformed the data because by default the scaling value is true. See, it is mentioned pre-process is true, right? Yes or no? So it pre-processes your data also. Because it is going to use a collection of models, don't you think pre-processing is mandatory? Scaling is mandatory?
Yes.
Because there will be collection of models like decision tree based, linear regression, linear model based like SVMs, logistic regression and all that. Imputation type you see is simple. Simple means that you are not using a model to impute. So if you have a numeric feature, it imputes it by mean. If you have a categorical feature, it imputes it by mode. So as long as your data is, you can say alphabet free, you can use this model directly, even if it has missing values and all that, it will take care of it. You're doing 10 folds. CPU jobs is -1, which means that it is going to utilize all the cores. Okay. And then there are certain things related. I don't have a GPU, so that's why it's set to false. If you had a GPU, a graphic card, it will be true and it will make use of that also. So it's a very excellent package, by the way. Now I'm going to show you what models are running. So you just type models and it shows you a list of models. Sorry, this is coming from the previous one. Okay, just a second. I have to see the syntax again. There is one command for this, which lets me looks at the models. It's the function brackets. Okay. The previous models are coming from lazy predict. Okay, 1 second. I have to import models also from here. So these are the models that are available to you. So you can see the name of the model. LR stands for logistic, K nearest neighbors, naive Bayes, decision tree, support vector machines, SVM with radial kernel, SVM with linear kernel, and so on. Okay, just give me a second. I'm sorry, guys. Yeah. So these are the models that are available to you. Now, how do you compare the performance of these models? All you have to do is type compare models. Okay. Sorry, it's called as compare models. Just a second. I think I need to import compare models also. Let me just see. Okay, is it a function or is it just a argument? Yeah, it's just compare models. I need to import this. So it's better to write this. Okay. Maybe I'm going to import star. Okay. Oh, sorry. It will not work like this. Okay. I think it's there in this only. Just mention it here. So now it is going to train these models one by one and show you the results. So as soon as it trains, you can see the results. Okay, they are getting generated. So these are the tenfold results. It is sorting the values as well. All right. It is sorting the values as well accordingly. So let it finish. And then I'll show you how to tune these models also. Okay. So even though it is running tenfolds, it is not tuning it right now. It is just doing it by running tenfolds and giving you the average performance. I'll show you how to tune one of these models, and that way you'll be able to, get an edge over these, like the best performing models. It will probably take around 2 to 3 more minutes. There is this model called as extra trees regressor that also does very well. Extra trees classifier, sorry. That also does very well, which takes a lot of time in comparison. So it's almost done. Just 2 more models remaining. Yeah, this is done. So it is highlighting, okay, what is the best performing model? In this case, you have CatBoost to be the best performing model. Okay. Can you see that the ones that we discussed are the best performing ones? The 3 extra packages that I told you. Okay. The 3 extra packages that I told you are the best performing ones. Okay. Maybe I'll show you for one of them. Okay. So let's say you want to tune this random forest classifier. Okay. So what you do is this. Just a second. So let's say I'm going to show you for one of them. Okay. So let's say I'm going to tune this. Select the name of the model. Okay. Let's say I'm going to tune this random forest classifier. So select the name of the model, which is RF. Okay. I'm going to tune this. What are the params that you have to specify? Do you remember you created this grid, right, of parameters when you wanted to tune any model in sklearn? So you just pass that grid. Okay, you just pass this grid. So let's say I'm going to pass this grid, or maybe something else which I can reuse. Just a second. Yeah, I will use this. Okay, because some of the hyperparameters match. Okay. So number of estimators is there. Learning rate is not there in random forest, so just remove it. This is called as max features, max samples, sorry, in random forest. Okay, max features is there, and then you have min sample split. So you can just pass, I think, this hyperparams here. Okay, so this has to be passed as a dictionary. Okay, just a second. Okay, I have to import this tune model also. Just a second. All right. Just a second. Okay, I have to run this again. Sorry, these are the. Okay, I just ran this right. Let it run. I just need to check this. I'll just paste this for you. Yeah, so just in case you want this documentation, so it'll be helpful for you guys. By the way, PyCaret can do a lot of things, okay? Not just your classification and there is a there's a passing custom grid. This is what I'm looking at. It's called as custom grid, not. Problem. Why does it say RF is not defined? Oh, do I have to pass it like this, like a quote? Please pass trained model object. Okay, just a second. Let me see. Okay, if okay, I have to create a model first. Okay, my bad. Okay, this is what I need. So first you have to create a model object. So this is my random forest model object. Okay. And then you can pass this, I believe, this object. Let's call this as RFC, random forest classifier, and then you can tune this. Arre Baba, so many times. Okay. I should have done it in the beginning itself. Yeah, maybe just give me a second. Okay. I should import everything from it. Otherwise, I have to import so many functions. Okay. All right. I think I can do this. I can do this now. So, yep. Okay, so now it is just giving you the results of the 10 folds, but it's doing a grid search on all of these values. Okay, it's doing a grid search on all of these values. So this is the results of the 10 folds. Okay, it is giving you the average as well. If you look at the results right now is how much? 96.47, right? For the accuracy. Do you see accuracy is 96.47?
Yeah.
Let's see how much was the accuracy for your random forest without the tuning. How much was it? 94.99.
Yeah.
So it did. So it's actually an easy package to use, but like use it only if you have a good machine. Okay, use it only if you have a good machine. My machine is fairly good in that regard, so I suggest that you use Colab for it. Colab will be appropriate. Don't run it on your machines if it is having less than 8 GB RAM.
Sure.
Okay. These are heavy packages. These are heavy packages. Okay. So this is some of the packages. Now, if you want to change anything, right? Let's say you want to do a regression experiment. replace wherever you see a classifier with a regressor in any of the models that we have seen. Okay. Wherever you see classification, replace it with regression. Wherever you see classifier, replace it with regressor. And rest everything will not change. Okay. Only the hyperparameters will change. Okay. So rest everything stays the same. So I'm not going to do for any regression data set separately. Will you guys be able to do it on your own? You just have to replace classification with regression and classifier with regressor. Rest everything will be the same. Okay. If you are facing trouble, then you let me know in the next class. And I'll show you how to do that as well. Okay.
Okay.
All right. All right. Let's see now how to combine say multiple models, and let's see how to do heterogeneous ensembling. Now, please note that I first advise you to get the best models. Okay, get the best version of your models. So whatever the best version of your models is, first get those. Okay. So train those. How many models do you want me to combine? Tell me, how many models do you want me to combine?
Maybe 3.
Okay, which ones do you want? Okay, tell me which ones do you want?
Linear regression.
Do you want me to do regression now, or do you want me to do classification? Shall I do it for regression, and then you can replace classification with
Yes,
regression?
yes, we
Okay.
can do
Okay.
that.
Maybe I'll take a regression data set now. Okay. All right. So I'm going to take one regression data set. Maybe say this one. Predicting the impact of diabetes. Okay. Okay. So we are doing for regression. So what is the first model that you want me to import?
Diabetes.
Let me first import it. Okay, I've imported my data. What is it that you want me to do?
Linear regression.
Linear regression. Okay, so first model is say linear regression. Anything else? Any other model? Tell me, which model do you want? Which one?
Logistic regression.
Logistic regression is not for regression, right? It's for classification. What else?
I can use decision tree regressor.
We can use decision tree regressor. Okay. Anything else?
The simplest k nearest neighbors.
K nearest neighbors. Okay. How many neighbors do you want for that?
3.
So, okay, let's go with K neighbors regressor. Okay. So let me first split the data into 2 parts. Okay. I'm not doing now 10-fold regression. Okay. 10-fold cross validation. I will just do like one train test split. Okay. Otherwise, it will just take time. Nothing special. So let's do train test split. So let's get the features for both train and test first. And the outputs of train and test. Once this is done, let's combine these models. So you want to combine these models, right? Let me call this as my ensemble. Okay. Let me call it say my ensemble. Let's call this. Okay. So you have to make this ensemble Just a second. So you have to make this ensemble as a collection of individual models, like the one we define it in pipeline steps. So the first model that we want is, let's say, linear regression. Let's call it, say, linear LR, and this is your linear regression model. Okay. The next model is going to be decision tree regressor. Let's call it, say, DTR, and use this decision tree regressor. Okay. And the next model is your this k-neighbors regressor. Let's call it, say, KNN. And I'm setting the number of neighbors as 3 as suggested. Okay. See, but my advice is, given the data set, you can figure out the best performing hyperparameters for each of the models, right? Yes or no?
Yes.
So first find the best performing models. Okay. So the first step should be to find it. Okay. Though I'm not doing it. Okay.
So that means I'll run each model individually and first tune that particular
Yes.
model, and
Then you combine the ensemble of those 3 models or 4 models, whatever you want to combine. Okay. Okay. All right. So I'm not tuning the models. I'm just combining the models directly. Now, what you need is a package called as voting classifier. So essentially, I want you to find the best hyperparameters combination for each of the individual models first. So you have to go to sklearn.ensemble, import something called as voting classifier. Okay, import something called as voting classifier. So use this voting classifier, and then you have to pass your ensemble here. Okay, and you have to provide the voting mechanism. So the hard voting mechanism means that you will essentially do the majority voting. You will essentially do the majority voting. Is that clear? So essentially, every model gets the same weightage, and if 2 of them it's not hard. I mean, in this case, we are doing regression, right? So you can say that you are doing simple averaging. Does that make sense? Yes or no? Is this part clear?
so that
What-
means whatever is the prediction from each model, we'll do the average of that.
You will do the average of those 3 predictions. Okay, and that will be the result. Is this clear? I just have to check if it is called as voting or something else. Okay, 1 second. So I shouldn't do classification. Okay, my bad. This is voting regressor, not classifier, since we are doing regression. Okay. I just need to check if it's called as voting or something else. Probably it's called as something else. Okay, not voting. It's called as, there is no voting as such. Okay, there is no voting as such. So by default, if you don't provide anything, it's simple averaging. Okay, by default, if you don't provide anything, it's called as simple averaging, and you can provide this estimators like this. Yeah, estimators like this. Okay, and then you can simply fit onto your data. So I'm fitting onto my training data. Okay, I'm fitting onto my training data and the train outputs. So this has fit the model, 3 models. Okay, and it is showing you for each of the models what are the hyperparameters that it is using. And then it is, you can use it to predict. Okay, you can use it to predict on the test set. These are your predictions on the test set. So currently it is doing simple averaging. Okay, and if you want to compute, say, any metric, which metric do you want me to compute, since we are doing regression now? Give me any metric.
Mean absolute error.
Okay, let's go with mean absolute error. Let's use this. So pass the actual values and the predicted values that you'll get from the model. I think I called my model as VC. Okay, and pass the test set to it. So this is the mean absolute error across all the predictions. Okay. So this way you can use this voting classifier. I'm going to show you one more thing. So when you're combining these models, right? When you're combining these models, you can actually assign the weights to these models. Okay, you can actually assign the weights to these models. Okay, so what do you think I should what do you think I should choose the weight of these models? So there is a component here, the hyperparameter here called as weights. So you can give a list of these weights. Like the first model should get how much, second model should get how much, and third model should get how much. Do you think I can actually decide based upon their individual performances?
Yes.
Okay, so I'm going to show you, if this was your voting classifier, you can get all the estimators like this. Okay, these are all your estimators. So if I do it like this, do you think that I'll get the first model linear regression?
Yeah.
Does that make sense? That's the first model, right? You have 3 estimators currently. Okay, you have 3 estimators. I think you can get it like this as well, if I'm not wrong. What name did we give to our estimators? I think we gave it as LR, right? No, you cannot access it like this. Okay, you can just
1, yeah, 0.
no, you can directly do it through an index. Okay, so this is a linear regression model. Let's say I want to know its performance. Okay, I want to know its performance. Don't you think I can use this model to get my predictions also?
Yes.
Okay, so I'm going to show you what is the prediction. Okay, using this model. See this carefully. So this will give you an estimate of how much the performance is using this model. Okay. Sorry. Just a second.
A dot.
Dot predict. I missed. Okay, so this is the prediction from your linear regression model. This is the trained model. Please remember, this is the trained model. Okay, that's why you're able to use predict on it. Otherwise, it will throw an error. Do you see that I can actually use the other models also? Yes or no?
Yeah.
Okay, so I'm going to use my second model, which is your what was the second model name?
Decision tree.
DTR.
DTR, right? Decision tree regressor. So let's see the decision tree regressor. How much performance we get from this DTR? This is the one. And if you look at the third one, which is this, the K neighbors. Let's get the results from the K neighbors. So this is this much. Now my question is, you have the performance of the 3 models, right? Which model do you think we should give a higher weightage? To which model we should give a higher weightage?
DTR, the decision.
Why? It should be the reverse, right? Lower the better.
The performance more will be the weight, right?
No, but we are computing mean absolute error here. Lower the better, right?
Okay, lower.
So it should be lower the better. So which one should get the highest weightage? Linear regression, right?
Yeah.
And what is the weightage? Can I say it is the inverse of mean absolute error? Yes or no? Okay. So you can give these weights as like this. Okay, I'm just going to show you how do you give the weights. So maybe I'm going to give these weights as 1 upon whatever is the mean absolute error. I'm just giving it like this, 1 upon 0.041. Does this make sense? Then the next weight would be 1 upon how much? For decision tree, it was this much, right?
Yeah.
Let me say 0.6951. Okay. 1 upon 0.6951. Okay. And the third one is 1 upon how much? This 0.31. Okay. You can give these numbers exactly also. There is no harm in it. Okay. You can give these numbers exactly, but now you are actually doing weighted averaging. Does this make sense?
Yes.
Yes.
So first of all, these weights would be normalized. First of all, these weights would be normalized. Okay. So that their sum is equal to 1. these weights have to be positive. Okay. So you can sum all the three and divide by the weights, right? Yes or no?
Yes.
So that way, internally it will do, and whatever is the final weight that you get here, that will be multiplied by the prediction of model 1. Whatever the weight that you get here will be multiplied by the prediction from model 2, and whatever weight that you get here will be multiplied by the prediction of model 3, and that the sum of these three values, weight into prediction for model 1, weight into prediction for model 2, weight into prediction for model 3, this will be the weighted averaging part. Okay, let's see. Okay, this is your voting. I should call it VR instead of calling it as VC. Okay, so this is your voting regressor, and now you can compute, say, the mean absolute error from this overall voting regressor. Hopefully, we'll be able to beat this value. Okay, this value that we got from our original one, 46.37. Our value should be lower than this. Okay, hopefully. All right, let's see this. They see our value is actually lower than this. And this makes sense, right? What was the value here? Around how much? 46.37, right? We were able to beat this value by, around 2.7 or something. Okay. So it's now 43.82. Lower the better, right? Remember this. So this way you can give weights to your all your models. All your individual models. Any questions about this?
So like each model I have different steps, right? In my ensemble, I have given 3 models. For first model, I have to do standardization. So I can create a pipeline within the ensemble.
So why don't you just standardize the whole data? Because decision trees are not going to be impacted by this, right? But for others, they will be. Yes or no?
Only decision tree is the model that doesn't take standard, like that doesn't require standard.
That doesn't require it, but if you feed it standardized data, will it have an impact? No. So better to standardize everything, right?
Okay.
Okay. So yeah, you're right that, okay, I forgot to standardize the data. So what I'll do is I'll standardize it here itself, and then you can run it. Yeah. I'm going to normalize it rather. Yes.
Now, whatever pipeline we have seen is generally we do the scaling and then applying the model.
Correct.
Anything else that is
there in the pipeline? Yeah, you can do imputation in the pipeline. Okay, you can even basically encode in the pipeline. Okay. If there are categorical features. So there are steps, right, that you think that you follow, right, when you are training any model. So any of those functions that you know can be applied in the pipeline. Okay. Okay, this time I'm going to do say min-max scalar. Hopefully you guys will be able to run it. Okay, so I'll just I'm going to do the scaling between 0 and 1, so I'm not providing any feature range. Okay, by default it scales the values between 0 and 1. Okay, I'm simply assigning it back to xtrain. Okay, so okay, and now you can run all these things. Okay, I'll just run this. So my data has been standardized. Okay, so it ran everything. Okay, so after standardization, this was the result. Sorry, after normalization, this was the result, 47.13. Then after merging the values, though these values would have changed slightly, but let's see what are the results now. It's around 44.83. So we still have a boost. Okay, we still have a boost. You can try with standardization also if that helps. Because k-nearest neighbors prefers normalization. You should do normalization when you're doing k-nearest neighbors, and standardization when you're doing linear models, like linear regression. Okay. So you try with both of them, whichever gives you best results, go with that. So this is your heterogeneous ensembling, and wherever you have seen a regressor, you replace it with a classifier. I'll just tell you one thing which is different between the two. Okay, between voting regressor and voting classifier, there is just one difference. Okay. Okay, and the difference is of this voting thing, which I was mentioning earlier, this voting thing. So if you are doing voting as hard, okay, this means that you are actually taking the majority vote. Is that part clear?
Yes.
And if you say voting is soft, then you want to give weights to these models. So where are the weights? In this weights. Okay, you can give say twice the weightage to the first model, then say one weightage to the second model and third weightage, I mean one weightage to the third model. So first model gets twice the weightage of the other two. Okay, so that way you can consider the weights here. So in classification, you have to specify it as soft to make it work. In regression, there is no concept of soft voting, right? Hard means, so I'll just mention it here, okay, in your notebook, okay? So if you are doing classification, all right, so hard here means that you are doing majority vote. And if you have soft as the voting mechanism, then you can provide weights, okay? Give weights to your models, okay? Okay. All right, so this is what you do. When you are voting hard, you can consider the weights to be 1, 1, and 1 for the 3 models. Okay. So this is for your classification. That's the only difference. Okay, that's the only difference. Any questions? Yes, people, any questions? So if you're, let's say, using classifiers, you can use the accuracy of the models. Maybe accuracy will give you an idea of the performance. Okay, you can use any precision recall also, depends on how you view it. Okay, not just accuracy, use any performance metric. Okay. Any other questions? Yes, any other questions about this, about these packages that I've shown you today? Anything that comes to mind? Thanks. Shall we discuss the next package?
Yeah.
Okay. You guys are up for it, right? I mean, I hope it's not like too overwhelming for the day. Okay, so let's do imbalance classification now, or skewed classification. So for this, you have to install a package called as IMBlearn or imbalance learn. Okay, this is the package that you have to install. It doesn't come installed by default. Okay, so install this package first. All right. So once you install this package, what you can do is, which technique do you want me to try? Which technique do you want me to try? Tell me.
Smart.
Which one?
K means smart or
Okay, no. I mean, start with the basic ones. Okay, not jump to k-means mode. I'll implement that as well. Don't worry. Okay, but let's start with the first technique. So oversampling or undersampling? Which one do you want me to try first? Which one?
oversampling.
Okay, let's start with oversampling. Let me show you how much is the. So let me first split the data also. Okay, 1 second. So I've just put the data set. I'm going to show you how much is the distribution of your train set. Okay, in the outputs, what is the distribution of the so which class is the majority?
1.
1 is the majority, right? As you can see, class 1 is the majority and 0 is the minority. Okay, so what we want to do is, what did you mention? Oversampling or undersampling?
Oversampling.
Okay, let's go with oversampling. So from IMD Learn, you have to import this package oversampling and you have to do random oversampler. Okay, call this function random oversampler. Now let's understand this random oversampler. Okay, so let me print this before. Okay, so print, I'm printing the counter of Y train before. Okay, so I'm going to print, okay, this was before, so that you can follow it. Okay, this is what has happened. Okay, so this was the distribution before, and now I'm going to call this a random oversampler. Okay, I'm going to call this random oversampler, and I have to provide this argument called as sampling strategy. So please see what this sampling strategy does. There are many inputs that you can provide to this. I'm going to show you what can happen if you provide real inputs to this. That is easy to understand. So I'm going to fit and resample. So basically you fit it onto the train set and the outputs. And what it will do is it will generate. So what is it that we want to do? We want to see in oversampling, what is it that we want to do?
Increase the
Duplicate.
We want to duplicate, right? We want to increase the minority class samples. Okay, basically we are duplicating them. Now, this function fit underscore resample, what it does is it will take the minority class examples, which is class 0, and it will increase this number. And it will retain this number 1, 249 samples of class 1 as it is. Okay. So do you think I need to pass outputs also when I'm sampling? You have to, right? Yes or no? Because you need the output of that sample which is being duplicated also, right? So what this will give you, you can say resampled data. Let's call it resampled X train and resampled Y train. So I want to show you in this resampled data. So this is generating resampled data, or rather I can call it upsampled, right? Yes or no? I've increased it, right? Yes or no? So what this sampling strategy 1 does, it will ensure that, please remember this, okay? Sampling strategy 1 here means that, okay, please remember this, okay? Sampling strategy 1 here means that, ensure that, okay, the minority class examples are equal to majority class examples. Does this make sense?
Yes.
Okay, so essentially what you are doing is the resultant minority class examples, okay, are nothing but sampling strategy multiplied by what number?
The difference in them?
No. What is sampling strategy right now?
1.
1. So it should be equal to majority class examples, right? Yes or no? This number should be multiplied with number of majority class examples, right? See, I want to increase the minority class examples, right? So how much minority class examples should increase? So if I'm saying sampling strategy is 1, if you multiply 1 with the number of majority class examples, don't you think the resultant minority class examples will become equal to majority?
Yes.
Okay, so that's what this formula means. Okay, so let's see the distribution afterwards. Okay, let's see the distribution afterwards. So this is the distribution afterwards. Okay, let's see. So it will print before and after what, sorry, I just printed for Y train. I have to print it for resampled Y train. Okay, what do you see now? 0 has increased to
249.
49. Okay, let's say I make it as 0.5. How many minority class examples will be there?
Half of the other one.
What half of
Half of what number? 249, right?
49.
59.
And how much is that number? 0.5 or 249? You can take the ceiling of,
125.
let's say 125. But you already have 149 samples, right? So do you think this function will allow you?
No.
See, otherwise it becomes downsampling, right? You have to but upsample, right?
Yes.
You have to increase it. You don't have to decrease it. So you will see that this will not allow. It will throw an error. Okay. What do you think it says? Read about this.
Ratio.
So it clearly says that please increase the ratio. Okay. You are actually trying to remove samples from the minority class, which is not correct. You have to increase it, right? So that's why it says that please increase the ratio. So if somebody asks you what is the least value possible for this sampling strategy, how do you compute it? Anyone?
149 divided by 249 we can do, and
That is the right number. Yeah. 149 divided by 249. This is the least sampling strategy. Okay. So this should be at least greater than 0.598. So if I put it as 0.6, this will work. Anything less than 0.6, it will not work. Okay. If I put it as 0.6, okay, where it is, this will work. Anything less than 0.6, this is not going to work. See, at 0.6 also it creates a problem. Let's see why. Because maybe if I make it as 0.6, right? How much is the number? If I multiply 0.6 with this, what was it? 250, what? 249.
49.
Okay. So this is 149.4. How much is the total value currently?
149.
149.
It says that you are neither increasing nor decreasing. At least one sample needs to increase, right?
Yes.
Okay. So you need to provide maybe say 0.61 to make sure that, okay, this becomes 150. Even if you do maybe say 0.605, that will still work. Yeah, this will work. If you provide 0.605, because at least one sample needs to increase. Okay. At least one sample needs to increase. Do you see that now?
Yes.
Okay. So now you have an understanding of what should be the minimum sampling strategy. Okay. So what we'll do now is we'll train a model with and without sampling and then see the results. Which model do you want me to train? Which model shall we train? Shall
Decision
we
tree.
go with logistic?
Decision.
Okay, let's go with logistic and then see if it is helping or not. Okay, I'll go with what's first one sampling strategy. Okay, when they both are equal. And then I'll show you it is not necessary with one that you get the best results. Or maybe you get the best results. I do not know. I'll have to check. So let me import logistic regression. Let's import this. I'm going with a default model, not tuning it. So let's give a random state to get the same results. And then I'm going to fit. Do you want me to scale it or is this fine? Do you want me to scale it?
Yes.
Okay, I'll scale it as well. Just a second, I'll keep it here then. I'll assign it to Xtrain again. Okay, so that way you don't have to change variable names. Okay, so fitting the model and computing the accuracy score from it directly.
Should I fit REX train or
Can you repeat, please?
in while fitting data to the model, should I fit the mod?
No, I'm currently doing it with, and then I'm doing it without oversampling.
Okay.
And then I'll show you with oversampling if it is helpful or not. Okay, because I have to compare the results for both of them, right? So this is without. Okay? This is without oversampling. So this is without oversampling. Let's get the results with oversampling. Okay, but predictions will be done on the test set only. Do you see it changed or not? It didn't change, right?
No.
You see the model doesn't change for this. Okay, what I'm going to do now is I'm going to try with the different sampling strategies. Okay, let's do that. So what should be in what range I should search? From 0.605 onwards, right? Yes or no?
Yes.
So I'm going to search from 0.605 onwards. I'll go up to 1, okay, and maybe take say 20 values in between. Okay, I'm trying in these sampling strategies. Okay, so let's say for I in this SS, these are my sampling strategies. And let me call the random oversampler method. Okay. So I'm calling this random oversampler method here, providing the sampling strategy as this I. So every time the sampling strategy will change, then I will upsample my data. Okay. So upsampling my data. So on the upsample data, I fit the model, compute the accuracies. Let me store all the accuracies in this folder called as, in this list called as ACC. And let me append these accuracies. Okay. So these are your accuracies, okay, of those 20 different sampling strategies. Any differences as such that you see? There are certain differences, right? Do you see that there are certain differences? Okay. So let's see, what is the best value? If let me get the max of ACC. It's the same, right? 97076.
Yes.
Okay, so maybe oversampling is not helping here. Okay, in this case, oversampling is not helping. Okay, maybe for this test set, it doesn't help. Okay, maybe if I just change this random state, this might help. Okay, let's see. So this is the distribution right now, 254, 144. Okay, this is the default value. So this is without oversampling. Come on, this is 99.41. How will we beat this? Okay, that becomes worse. Okay, let me do one thing. Okay, let's try with some other random state. Okay. Yeah, this is 249, 149. Okay, this is 97.66. Actually, with if you increase it, then the results actually go down. Okay, let's see with different sampling strategies. These are the results that we get. Okay, let's see if we can increase it better. I think it's the same, 97.66 again. This was the result. Okay. 97.66, 608, right? Yeah, it's the same results. Okay, so it's not helping. So I just want to show you, like if you do it say 10 times or like over 10-fold cross validation, this will help for sure. Okay. In some case, the results would be better. Okay, and the averaging would come out to be slightly better. So oversampling can help. Okay, oversampling can help. Maybe I'll take a different data set just to show you. Okay, let me use this one. Okay, this is a relatively bigger one. Okay, let's take this. Fetch California housing. Okay, this is a relatively bigger one. These are all small data sets. Okay. This one has around 20K samples. I don't have to change much. Okay. Just a second. What's the problem?
Data sets.
Data sets. Yeah, data sets. Thank you. Okay. We are doing classification. My bad. Sorry. Sorry. We need Okay, what do we do? Let me just go through these data sets quickly, okay? It's a faces data set, news groups, too much, too big of a data sets. So there a smaller one. See, 47,000 features, okay? I mean, we might okay, just a sec.
Go with that iris one so that we can also see if we have more than 2 classes, then how is
Yeah,
the
that okay, yeah, that you can also do. Okay, that you can also do. Okay, let's go with this iris then. It will change the values for all the minority for the minority examples. Okay, for the minority classes. Okay, let's load this iris. But iris again is a small one. Okay, either I should increase the test size so that you see the results. Okay, all right. So can you see that now there are 3 classes? This is the distribution of your train. Okay, I'm going to run it. So this will 1 second. Okay, what does it say? So we have to increase the sampling strategy probably. Okay,
very less difference in
just
the
a second. You have to use a dictionary here for multi-class. Okay, so here you have to use a dictionary. Okay, so for class 0, how much do you want? So you have to use a dictionary. For what class do you want to do it? For what class do you want to do it?
0 only because
Okay, if you want to do it for 0, what sampling strategy should we have?
so it should be
Can we make it
32.
0.9?
Hmm.
See, what is the majority class right now?
37.
So 0.9 of 37 would be how much? 9 7s are 63, 9 3s are 27, 33, right? So it will work. Okay, this will work. Okay, maybe slightly increase it. That's what it says. Yeah, I need to. So it is 32 point something. So maybe I have to make it say 0.95. Okay, it still doesn't work. Just a second. With oversampling methods, the number of samples should be, yeah, that is true. There is 32 samples and, oh, you have to mention the exact number here. Okay. This time it says that you have to mention the exact number. Let me put, say, 35. Okay. Do you see that now class 0 became 35?
So here, rather than giving that ratio, I'm directly mentioning what
Yes.
records I want for class 0. How many records?
For multi-class, yes, this is what you have to provide. Okay, maybe I'll just say that class 1 also becomes say 37. Okay, just to show you that. Okay, you can change for class 1 also. Okay, so you can provide the numbers here directly. Okay, so provide the numbers for multi-class. All right, so if I do this, let's see with. So this is with, sorry, this is without, this is with. Okay, doesn't help. Okay, let's look at the accuracies. Okay, just a second. What's the problem? Maybe sampling strategies. I have to provide it like this, right? I have to give dictionaries now. Okay, that's why it's not helping. I'll go back and use the same data set again. Just a second. I'm using the same data set again, but I'm changing this number. Okay, I'm going to put 60% in my test data. Okay, that way I have a lot of samples and only 40 samples in my 40% in my train. Okay, just a second. I have to increase this number.
Now again the dictionary.
Yeah, dictionary thing. Yeah, I'll just ensure this. This is say 0.7. Or maybe I'll show you just, okay, this is 1. So this is the result. So this is without oversampling and this is with oversampling. Okay. Do you see that oversampling helps now?
Yes.
So see, if the data is more, then obviously on 1 or 2 samples, it will help, right? Previously, the data was less and you were already doing 97% approx. Let's see for different sampling strategy if we can even beat this. So it is around 97.07. You can see we find a sampling strategy which is even better than this. Does that make sense? And what is this sampling strategy? Let's get it. Okay, so ACC dot index of this maximum value. And you have to get the SS of this. So at this much sampling strategy, you get the best results, which is around 97.076. So this is what I wanted to show you. Oversampling will help. Okay. We'll do the remaining tomorrow. So I'll stop here. Any questions? We'll do the remaining tomorrow. I'll stop here. Any questions?
No.
So I'll just upload this. Let's discuss tomorrow about the remaining imbalance classification strategies. All right. If you have any questions, you can stay back and ask. Otherwise, I'll just upload it, this file to your drive folder. Sorry. Okay, guys, we'll meet tomorrow then. Bye-bye.